Here we are. So anyway, so today we're going to talk about the DNS, right? And DNS is sitting somewhere uh, at the application level. Yes, because DNS is using UDP, but somehow it provides support to the application. All right. Well, we'll try to understand what is exactly that system, which is hard to understand. Why? Because it refers to so many things. All right. So it's not just a protocol. It's not just a server. It's not just a database. Is everything. So it's a complete system. So let's try to understand what it is. So first of all, the DNS, the main objective is to provide with internet users with a kind of a phone book, yellow pages. All right. So what it means that I need to be able to provide the name of a host, and giving the name, I need the IP address. Because as I said, even if as a user, you may able to connect to a server just by providing its name, the name is not good enough. Okay, when your message is going to go through the IP layer, you need to have the IP. The same way when you make a phone call, the name itself is not enough, right? Somehow you need to know the phone number. The same goes for the computers. So we'll see that actually DNS is using a lot of concepts. So first of all, indirection, as I said, we allow users to use names instead of IP addresses. That's great. The fact that there's the hierarchy, which means that we will see that the names follow somehow labels, and those labels, as you may see, end by a domain, which is bigger than the next label, and so on. So we'll see that not only the names have a hierarchy, but as well the servers themselves, which are connected together in order to resolve the requests. And also caching. We already saw that in HTTP or the web, we need caching to improve the performance. So here is pretty much the same. So for DNS, the performance of DNS highly rely on caching. Okay, so three concepts, and you see, so that's huge. The other thing that we're going to see is, okay, so how DNS is working on a host. So there's a software called the Resolver included in your operating system, and servers on the other side. So we will see that there's a bunch of servers, and all of them are not equal, okay? Because we have a root and so on, multiple levels. That we have then queries, and here too, to resolve a query, we have multiple ways of doing this. And the caching specifically to DNS is TTL based, which means that actually whenever we receive some object, okay, we're going to have a TTL, which means the expiration date, which is not the case for the web. So that's the reason in the web, we always need to check, oh, is that object fresh enough? No, here it will come like the milk. There will be a date of expiration, meaning that it could be available for a year or 1 year, 1 hour, 1 week. So the TTL is included. So we don't have questions such as, is it fresh? No, we know it's fresh. And the last thing is to see how DNS may impact on the web, the same way we already studied TCP and the web. So here we'll see that DNS is partly have a huge impact on the performance of the web. All right. So first of all, we talked about the name, okay? As you may remember, and we will see that later, any host on the internet, any machine needs an IP address. That's the way it works. So you can say it as a phone number. So an IP address is a binary value, okay? For IPv4, because we'll see that actually we have two versions, is a 32-bit long ID. And that ID is related to the location. So it means that if you move your computer, your IP need to be updated. So you cannot reuse the same IP the same way you use your phone number and you roam from China to another place. You need to change your IP. So whenever you're home, the IP address is, so here I give a few examples, and they are hierarchical as we saw in the previous assignment, knowing that we have a prefix, and the prefix is the information regarding which network are you connected to. So that's the reason if you attach to another network, that prefix will change. And as you may see here by the bold characters, is the fact that that prefix have a different length, okay? It depends on the network. Okay, so those for the IP addresses, we're going to get into much more details. But as you may see, and you probably have seen them before, we use a dot decimal notation, which means that 1 byte is converted to the decimal value, and each byte, we have 4 in total. Since IPv4 addresses are 32-bit long, I always provided this way because they are user-friendly. But basically, it's 32 bits, all right? On the other side, as a user, we are using names. Names have a lot of benefits. First, it's easier for you humans, users, to handle names, okay? And we may remember the names easily, right? I want to connect to nyu.edu. Well, the name makes sense, giving which server do I need. The length is totally viable, and we use some specific characters, but mainly we can use letters, numbers, and so on. And for names, even though IP addresses are strictly related to your location, and giving your IP address, I can know quite precisely where's your location. With a name, is not so obvious, all right? So if I have nyu.edu, where is the server, okay? Very hard to tell. If it's a .com, is it located in the US, somewhere else? So we have very little information regarding the location, and basically that's not really the purpose of those names, even though the domain may give away some information regarding the location, okay? But it doesn't have to follow this. So it's not because it's a .cn, it has to be in China. No, you can have a .cn and be located somewhere else. But the IP address won't lie. Okay, so as you may see, so on one side we have the name, and on the other side we have the address. So, okay, we already said the name is pretty handy for a user. It's much easier than remembering all the IP addresses. But there are also other benefits, and we'll go over them now. So, okay, so we can remember a name more easily. That makes a lot of things. But actually, what may happen, your IP address may change. And in case of a change, though your IP address may change, if you move from one network to another, if you change your internet provider, okay, you cannot use the same IP from one provider to another. So it means that even though the IP address may change, it doesn't have to actually change your name. So you can keep using the same name, though the IP may be updated. And so that's very handy because basically when you have an application, instead of putting the IP address hard-coded, you don't hardline the IP address inside your application, but you'd rather have the name. So it means that even in the future, the IP address may be updated, using the name actually will prevent you from changing and updating your application whenever the IP address change, all right? So first of all, that's a way of making everything transparent regarding the IP address. So that's a good point. The other thing is the fact that for a single name, you may have multiple IP addresses. What do we mean by that? We mean that most big websites, such as Google, for instance, actually rely on multiple replicas. So all of them share the same name, but actually those are different multiple servers across the internet, okay? So you will hide this to your user. So it means that I'm trying to connect to Google. Should I be aware that actually there are multiple servers and I need to select one of them? No, as a user, I don't really care about this. So hiding the details of the IP addresses and the fact that I have multiple mirrors or replicas, it's quite handy. And this is thanks to the names. Otherwise, as a user, I need to provide with a list of IP addresses, and then it's up to you. So which one do you want to choose? Oh, I don't know how. So you see, so those kind of details are hidden to the users. Obviously, having multiple replicas is, for some purpose, is somehow, it means that having multiple servers bring the benefit of doing load balancing, which means that you can share the load of all the requests for many servers. So for Google, it's pretty handy because you don't need to overload one server. So you have multiple servers to share the load. For the user, if your request is redirected to the closest server, it may also have a benefit, given that, yeah, you're probably gonna get the content for somewhere which is really close to you. So there are benefits for the client, but also for whoever is running the servers, all right? So names will hide those details. And also what you may have is one IP address, one server with multiple names. So which means that thanks to the name, you may refer to a different service hosted. So even though the IP is the same, the name will be, you will be able through the name to use a different service hosted by the same server. So as you may see, the fact that here you have an interaction, and for one name you can have multiple IPs, or one IP, multiple names, brings a lot of benefits. All right. So, okay, so as we may see, so since we have the names, but at the end I need to resolve them in the IP address, the corresponding IP address, or a list of IP addresses, it means that I need a system at least to do the resolution, all right, to handle my request. But actually, when we refer to DNS, DNS is so many different things. And that's the reason if you read online, they may talk about the DNS regarding one of those things. But basically, DNS is all of this. So what do we have? First, a naming scheme. And you may see that any name comes with labels separated by a dot. And usually, on the right, you have the domain, like either the country, or if it's a .net, edu, and so on. And you have multiple other labels, okay, which may make sense, may not make sense, okay. But usually, for instance, you have CS for the computer science department, .NYU for New York University, .edu because it's a university, all right. So there's a kind of a hierarchy here, all right. The other thing is, since we need to handle name, we need to ask who is in charge of allocating the names, because the names need to be unique. So let's say I have a server, I need to give my server a name. Who is in charge of actually checking the names that I'm going to use, all right? So there's an allocation policy here for the name. Then once you decided about the name, you need to have a database where you're going to have for that host name, the IP address, the corresponding one. So that database, we will see that in the case of DNS, is not centralized, is distributed, obviously. Otherwise, the database would be huge, and you cannot possibly, as we will see, host it in a single server, okay? So it's distributed because you have a collection of servers, all right? So you have two things. You have the fact that each servers are usually replicated. So you have a primary server plus multiple backup servers. But as well, we will see that the database actually is divided in pieces, and each piece is taken in charge by a server. So one server doesn't have all the mappings of all the names of the internet, but you divide the database on multiple pieces. And then obviously, since a client needs to interact with the server to resolve a name, what do you need? You need a protocol in order to request and respond to a request. So that is what is DNS. So you see, that's a huge system, okay? So to study DNS, we need first to go over the properties, okay? So how are the names organized in different domains? So we need to understand why do we divide them in domains. Then we will try to understand how the servers actually are organized together, how they are connected together. And then introduce on the top the root. The next level is the TLDs for top level domains. And then the last level will be the authoritative DNS servers. So we'll try to explain each of them, given that you have a nice tree. On top, you have the root, next level, and so on, so multiple levels, okay? And at the bottom, that's where you have the authoritative DNS servers, okay? On top of this, we have a proxy, which is also called the local DNS server, and we will try to understand why between me as a client and the root, which is the top of the servers, why do I need to put in the middle the local DNS servers? Okay, so let's make an assumption, okay, in order to motivate the reason we have these multiple servers and how it organized. Let's first make an assumption and consider that we have a single centralized DNS server for all the internet. So it means that any name you want to resolve is included in the database of that place. So what is the issue with having a centralized solution is the fact that we're not the only one requesting something. Oops. So if everybody need to rely on a single server, it isn't going to scale, obviously, because we have millions of requests per second for DNS. It's going to have a very high traffic volume, so it means that it's going to be overloaded, okay? It's a single point of failure, which means that if the server fails, you cannot connect to the internet anymore or maybe you know the IP address of the servers that you want to connect to, but if that server falls, right, it fails, that's the end of it. And of course, a single point of update, given that that database need to be updated every day, because every day you are creating new servers with new names. So you need to add the mapping of that name with the IP address. So even during the updates, which will bring a lot of overload on the server. So if a centralized one is not good enough, what should we do? We should basically find a way of replicating. Okay, so let's say we're going to replicate the server. So it means that all the database is duplicated on all those servers. Seems okay because it's not centralized anymore. So at least it is scalable. But now we have the following issue. It means that whenever I need to make an update, so if I have 100 servers, I need to find a way to synchronize all the servers together. So it means that if I have 100 of them, I need to connect to the 100 of servers and make the update or the change to all of them. Okay? So you see, so that is awkward, right? I mean, it doesn't going to scale because doing updates will be a big issue. So the other thing that I can do is also ask the question, okay, so I have so many choices, which one should I use? Because if the purpose here is to load to balance the load of requests, so I need to make sure that each client is redirected in such a way that actually you can spread the load of the request on all servers. Okay. So instead of doing this, the choice that have been made in the design choice that we made in DNS is the fact that we're going to divide the database in multiple pieces. So we have segments, portion of the database, and each server will be in charge of specific names in the internet. Okay. And we did it by saying that, okay, we're going to define multiple domains. So we have the names.com, the names.org, the names.net, and so on. And any server which actually belongs to those domains will actually have the mapping in the corresponding server. So still, we're going to replicate the servers within each domain because we need a primary and secondary, but synchronizing them is not too much of a hassle because we have like one primary, maybe two backups, right? So synchronizing 3 servers is not a big deal. But now the new question that we have, since this is scalable, but it's scalable only if when I have here a name, I need to be redirected to which server? To this one. So how can a client know which server actually should I request depending on the name that I need to request? Let's make an assumption here, and we have the list here of all the servers for CN, the servers for COM, and so on, and the IP address of those servers. So I check in the file and I say, okay, it's a .cn, who is in charge of CN? So why shouldn't we have this kind of file here? What is the problem of maintaining the list here? Absolutely. So you need to understand that every year we have new domains that are created. Okay? The .pizza, the .paris, the .berlin. So every year there's a kind of big opening where anybody can submit the creation of a new domain. So it means that if you need to update this list, it means that this list is installed in all the clients of the internet. It means that whenever you have a single update, you need to update all the hosts in the world. You know, so that's not really feasible because then you need to know, okay, where should I download that list? And then you have a new issue. So if everybody needs to download from the same server that file, so then that server going to be overloaded. And how often should I check if the file is updated? So you see, so that is a big issue. So that's the reason instead of having this, what we proposed, as Aline just said, I will have a root server on top of the TLDs of the domains. And the role of this guy is to have the list that we just talked about. So it means that I have one root server. So in my case, I know the root, and the root know all the TLDs, the top level servers. Okay? So the roots, hopefully, they don't change so often. They almost never change, hopefully. And if I need to update the list of the TLDs, I have a single point of change. I just need to connect to the root and change that. All right? So that is, you see, we'll solve a lot of problems. So, and then the CN is in charge of knowing the servers who are actually in charge of the domain that I want to resolve. So it means that the .cn doesn't handle any other IP addresses for the servers, but all names of Baidu. So it means that Baidu as a company, if they have web servers and so on, that I want people to learn the IP about, they need to maintain an authoritative server where they're going to create as many entries as they want regarding each of the servers that are hosted by Baidu. Okay? So the only thing that needs to be known here above is what is the IP address of the DNS server of Baidu that we call authoritative, because whenever you create a mapping, this is where you can do it and where Baidu is allowed to do it. So you see the multiple steps. So another problem that we may have to complete here the architecture is between the root and the client, given that you may have a lot of clients. So let's say if it's a NYU campus, you may see that there may be multiple requests for the same name. So obviously, we already said that our browsers have all a DNS cache. But the interesting thing is any network should provide a local DNS server, which is just a proxy, which means that you're going to aggregate all the requests at that server, which is provided by your company or your institution. And the role of this guy is to know the root. And so it means that before you're going to bother the root, first of all, you have cache here. So it means that you're going to check the caches. And if you don't have any information, you may go bother the root with this. Okay? Actually, the idea here is to say that most often we all connect 90% of the websites that we connect to are the same. You understand? So it means that if we all do the same request and we're using caching, it could be very powerful here to have some caching for all the host or the clients inside an institution. All right. So now we have this kind of architecture here. So what do we have? We have the root. The root knows the IPs of the next level here, which is the TLDs, the top level domains. And each of the top level domains, they need to know the authoritative domain server, who you can actually request the IP address of a server. So if you need to connect to nyu.edu, first of all, as a client, you will go to your local DNS server. If the cache, there's a miss, you don't have a hit, you're going to go to the root. Then the root will basically send you back the IP address of the server for EDU. So then you will go to EDU. EDU going to tell you, oh, this is the IP of the server that handles all the NYU websites or whatever servers, and then you will go there. So you see, so your request going to take multiple steps in order to discover who is the next step server that you should be requesting. But as you may see at the beginning, the only information that you need to know is the root. That's it. So this is scalable. So whatever the number of TLDs, whatever the number of domains, doesn't going to affect the states that you need to maintain. Because the more states, the more you need to update them. And the more updates, the more problematic it is. Okay, so we try to reduce the number of states that you maintain, and you share the information and you distribute it to multiple servers. Okay, so let's start with the roots. If you don't have any question, let's see about the root. So first of all, the root, we have only 13 of them. So obviously we have 13 because they need to be many of them to be robust, because if one is down, I need to find a backup. So yeah, the magical number here is 13. As you may see, 10 of them are in the US, in North America. All right, this is where they are maintained. And we have 3 other locations, one in Japan, one in 2 in Europe. All right, the main root servers are there. So which means that now, if I need to send a request and I need to go through a route, so if one route doesn't answer, I'm going to try the second one, the third one, and so on until one of the routes answer. And out of the 13, hopefully, okay, somebody will answer. Okay. So those are the routes. So they are all replicated. So they have exactly the same information. So somebody is in charge of synchronizing the entries in the route. But the only entries that you have in the route regards the TLDs. Okay. So whenever you create a new domain, you will need to add that new entry in the root. Once again, the only IP addresses that are maintained at the root are the IP addresses of the TLD's DNS server. Okay, so that is about the roots. Then what do we have? We have the TLDs. And the TLDs, once again, they are just for either the generic domains, they are still at the top, okay, like .com, .org, .edu, or the country domains. Okay, so some of them have been created as well. Okay, so those servers are maintained by some companies. For instance, for the .com, it's a company who is in charge of running that DNS server, that TLD DNS server, VeriSign. And for edu, it's a company which is Educos. Okay. Anyway, so those are changing. It's, for instance, for .com, before it used to be, I think, the Network Solutions, and now it's VeriSign. Okay. Anyway, so we have the TLD. And the role of the TLD is, once again, even if you ask him for the IP of Google, he doesn't know this. All he knows is the official DNS servers maintained by, for each of those domains, either Google, Amazon, Baidu, whoever. And we're going to redirect the request, depending on which domain, to the next following server. So you may see that here, the number of states are even increasing, because as many domains that you have for .com, as many DNS servers should be maintained by the TLD. Okay. So finally, the authoritative are the ones who actually will provide you with the IP address of the servers that you're looking for. Okay. So that is at the final stage. Okay. On top of this, I already said that, yeah, as a client, you're not supposed to go bother the root. Otherwise, the root will be overwhelmed. Okay. So it's not per se part of this, the DNS servers. This is more of a proxy, okay, that you put in between the clients and the root servers. So instead of sending your query right away, you're going to first go through a default DNS server. So you're going to ask me, yeah, but how do I know about my my local DNS? Well, we will see that the same way you learn about your IP address using a special protocol, which is DHCP. Okay, DHCP will provide you also with the IP address of the local DNS server. All right. You may also want to configure. So Google, for instance, can provide you with a local DNS server, which is that belongs to Google. Okay, and this is the IP address that you may want to configure instead of using the one of your ISP. Okay, but any local network, whenever you connect, is supposed to provide with the IP address of a local DNS server. All right. So it's either your ISP or your company or your university or the coffee shop that you connect to. They always need to provide you with the IP address of the specific local DNS server that you may want to use. If you try to bypass the local DNS server, most of the time, what's going to happen is the fact that the firewall is going to block your DNS request. We do everything that it takes to protect the roots. So as a client, so whenever you have a query, you will send it first to your local DNS server. And as I said, if you try to bypass the local DNS server, most of the ISPs or even your company will basically block your IP your request. Okay. The good thing about having a local DNS server is like they have local caches, just as your browser. okay? But on top of the caches that you use at your browser, they may be more effective because they are shared by a lot of clients belonging to the same institution, okay? And so the purpose of the local DNS server is to know the 13 routes and to redirect your request to one of those routes, okay? So when you use your DNS, okay, so what it means that, as we said, you have a local DNS server and your client, okay, the application that you're using, all right, will basically extract the name, either the one you submitted in your browser or the one that is provided in the application, and it will send basically that request to the local DNS server, right? On the server side, since you're the one connecting to the server, right? Once you know its IP, the server doesn't need to know your name because the IP is already provided in the request. So the DNS is mainly used by the client to learn about the IP address of the servers. So here we are. So we have multiple levels here, all right? And as you may see, so let's say you want to find one of the IPs of one of the Amazon.com servers, for instance, kindle.amazon.com. So you see, so your request need to go to the root, will follow that path. So basically, as you may see, at each level, you have multiple choices. So how can you tell which branch should you go on, given that you have multiple children at each level? So what basically tells to DNS that, oh, from the com I need to go to Amazon, from Amazon I need to go to Kindle, and so on. How can I do this? It's just included in the name that you want to resolve. Each of the labels, com, Amazon, Kindle. So each time you visit one of them, the next level is given by the next label. So I think that it's pretty interesting here to see that the structure of the name tells you which server should you visit. But you see that because you have a tree, that explains the structure of the name. So can you have a different scheme for the naming? Not really, because you have a tree with multiple levels. And each time you need to decide where to go. There are other systems that we're going to see with peer-to-peer systems, which are not using DNS, that organize the trees in a different way. Okay? Example, they do a ring. So the servers are connected by a ring, another tree. So there are other ways of doing this, okay? And so the name's going to be different, okay? But in the internet, once again, labels, each label refers to one of the servers at each level, all right? But usually here we have the TLDs and then the next level below that TLD. All right. So we talked about the resolution. So we have two ways of doing this. We have the iterative way and the recursive. So what it means, let's say I have a host here. So I didn't put the local DNS yet, but it works if you add the local DNS. So when it's iterative, it means that you go ask the root. The root will give you with the IP address of the TLD that you are looking for. Then, based on the IP of the TLD, you're going to ask the TLD for the next level, and so on. So you see there's a kind of a star here, and you need to go back each time to the client. All right? So here it is, this way. All right? When you do the recursive, what does it mean? It means that you have the host, you ask the root to handle your request. And so then obviously from the root gonna go to the next one, to this one, and back again with the IP address that you were looking for. Do you see the two modes? I think that is pretty obvious, right? So just a quick question. So which one do you think have more benefits? Do you think that, would you go with this one, and why? Why it is the one on the left more efficient? Can you tell? So you see, the only thing is, if you have a cache here, it means that you can cache all the answers. In this case, in your cache, you have what? Only the root and the final IP. So which means that anytime you have a new request, you still need to go to the root over again. But this way, if you learn about the TLD of the .fr, your cache will have all the details of all the servers, right? So anyway, nowadays what we do a hybrid. So what it means by hybrid? So first of all, we have a local DNS server, as I said. So it means that when I send here my request, I ask the local DNS to handle the request, and I'm waiting till I get finally the IP address that I was looking for. And that's the only thing that the client will learn about. So this is recursive. And the rest, what can you tell about this, is iterative. Okay? So you may see that this is a mix of the two modes. Okay? And as you may see, the cache here will have all the IP addresses for the others. All right? Okay, so once again, DNS is using UDP. So we saw that HTTP is using basically, HTTP is using TCP because it needs to be reliable. But one of the problems with TCP, we already said that TCP needs a connection. So it means that now, if you DNS use TCP, it means that for any request, the servers, including the root, the TLDs, and so on, will need to maintain a connection for each of the requests. And you see that at some point, a server, a TLD such as a .com, may receiving a lot of requests. So if you need to maintain a TCP connection for all of them, that's impossible. So that's the reason, since TCP have a connection, cannot use that one. So the only choice left is UDP, but UDP is not good enough because it's not reliable. So if UDP cannot make, can repair the losses or whatever, so it means that DNS need to be reliable. And so that's the reason we integrated in DNS some stuff like a timer. So which means that whenever I'm sending a request, if I'm not receiving the answer within a timer, I need to retry. And when I'm going to retry, I'm going to try with a different replica for that server. So let's say the local DNS, we said, need to contact the root. So first, I try with the root. That root doesn't answer. Okay, let me try with the second one. And what I have as well is before 2 tries, I'm going to have what we call the exponential backoff, which means that maybe the reason for not answering is because the root is overloaded. So in order to avoid making things worse, when I'm going to try later, I'm going to wait even longer. And I'm going to try up to 16 times. After 16 times, I give up. Something is wrong, all right? So that's the reason here, DNS is reliable by itself just because it have a timer. It uses an exponential backoff, and you have a list of servers that you need to try. Each time you need to try again, all right? So we could have done the same with UDP. So it means that UDP could have been on top of UDP, okay? And HTTP could be reliable. Well, no, we use TCP, okay? So any application, it doesn't mean that the application, because it's on top of UDP, okay, it doesn't mean that it's not reliable. Maybe everything that is related to making things reliable may be encoded in the application. Okay, so be careful with this, because some people will say, oh, on top of UDP, oh, that sucks. It's not reliable. You're having a lot of losses. No, I design my own mechanisms, okay? All right, so the caching, as we already said, so something that we didn't talk about when we talked about the caching is the fact that any answer, any response that I get, which is usually a mapping, so either for a name, I have an IP, or either for a name, I have the DNS servers, those mappings come with a TTL. The TTL is defined by whoever created the mapping, okay? So let's say I'm working in a company like nyu.edu. I'm creating a new server without that domain. I need to enter the name of that new server plus its IP. I need to provide a TTL. It's my job to say for how long those information are valid. So whenever I get a request for that mapping, I will provide the TTL, okay? So the TTL is used by the caches, including the ones on my browser, such as whenever I did a DNS request, I may keep that information for the duration of the TTL. And you know something? For instance, I'm going to go back to Google. For Chrome, for instance, they even play tricks on your back because what they do, they don't check the TTL. They keep it forever because they know that most of the time the TTL is a very conservative value. Okay, I'm going to say 1 hour, even though it's going to be available for 1 day or a year. So what they're going to do is like, instead of saying that, oh my God, the TTL have expired, I need to do DNS again, because DNS take a lot of time. What they do, they say, well, what the heck, keep it there. We're going to try. If it works, that's perfect because the user going to be super happy. Even though they don't really apply the procedure as it should be, TTL that expire, you should remove that entry, okay? Well, Chrome is doing those kind of tricks. And as we said, we have negative caching on top of this, which means like remembering about the things that didn't work in the past in order to how do you say, in order to avoid overloading the root with malformed names. So one of the things that you need to understand again is like DNS is a database. What we have the name, we have the type, we have the class, we have the TTL, yeah, makes sense, and the value. And the value and the name will depend on the class. So be careful, the information inside one of those records will depend on the class. So first of all, on the type. Well, why? Because the DNS was not designed just for the internet. Okay, it was a general system that may be used by any network, including the internet. So first of all, if it's IN here, the value IN, it means that this record have been created for the internet. Okay, but don't worry, internet is the only example of network that use DNS. Right? Then what do we have? We have the type, the different types. So we can have the type A. The type A is what makes the most sense to you, which means that I have a name here, www.nyu.edu. The value going to be the IP address of the web server of nyu.edu. So that is the type A. But type A is not the only one. What do we have? We have, for instance, the type MX. Yeah, because when you try to send an email, I need to send the email to a server, to a mail server. How can I know what is the IP address of the mail server of NYU? Well, anyway, this is Google, but anyway, but let's say I have my own mailing service, right? Well, the MX, the value gonna be the IP for the @nyu.edu. So not only your browser is using DNS, but also your mailer. So whenever you try to send an email, depending on the domain that you have, you're going to issue a DNS request asking for the IP address of the receiving mailing server. So DNS is not only for the web, also for the mail. All right, makes sense? All right, so that's the type MX. And that is the type that is requested by your mailer, which one, Outlook or whatever you are using, okay? Then we have another one, which is the CNAME. The CNAME refers to the canonical name. Why? Because most of the servers, most of the names that you handle, like www.something, those are just aliases. So it means that this is not the real name. Most of the time within your domain, what do you have? Your machine, that server, have a generic name. And on top of this, you may provide them with extra names. And the first thing that you need to do, and if you do that, for instance, for Baidu is not the real name of the machine, okay? This is just like a nickname. So it means that the first thing that you will ask for is, if you ask for the IP address of Baidu, they're gonna say, Baidu doesn't exist. You need to request the official name. And so what is the official name is W Shifen. And that is the real name of the server. And starting from there, you're going to ask for the IP address. So that's the reason there's multiple levels, giving that first, you need to know the official name, the canonical name, and so on. So that's the reason you have the type CNAME. And then you have the type NS, because you remember that most of the time, you need to learn about the IP address of all the DNS servers before you reach the last one, who can give you with the type A. So before you can receive the type A with the IP address of Baidu, you need to go over the root, the TLD, the authoritative server of Baidu, and so on. So to receive the IP address of the servers, of the DNS servers, you will receive a bunch of NS, name servers. Okay? Makes sense for those 4 types? That's the way it is. Then we have a protocol. So the protocol is rather simple as well. So as we may see, so we have multiple information here, including some flags. So the flags are just like bits that are set, so at a specific position, the first one, the second one, and so on. And they may help you into, for instance, tell if it's a query or reply, because the same format is used for the queries and the replies. The messages are the same. So the only thing that you're going to change between a query and a reply is 1 bit that will be set or not set. What kind of do you want to do the recursion or not? This kind of stuff. But anyway, there's an identification here. So it means that when I send a request, in order to receive the response and to match a response with the query, I have the identification. So that's a number that will basically match a query with its response. And as you may see, inside one query, you may have multiple questions. So that's the number of questions that you have. Question. And if it's an answer, so if it's a query, that's going to be 0. If it's an answer, you can also receive multiple answers. Okay? And so on. So we're going to see detail during the lab. Don't worry, next week. So I give you some further details here. You may read. But anyway, when you have the question section here and the answer question, here you have a specific structure to provide the information that you need to request. And when you have a query, the things that you have goes as follow. So the question section is a record which actually is missing some data, like the TTL, the value, because that's what you're requesting for. But whenever you send a request, you're going to provide the name you're trying to resolve. You're going to provide the type that you need. Is it the type A? Is it the type NS? And the class. Is it internet or not internet? Is it A? And so on. All right? So the type here is 2 bytes. The class is 2 bytes. The name is variable. And we have a special coding that we use in order to provide the names. And we give the labels. So we start with the size of each of the labels. And this is the end. And in the middle, I give the ASCII code for any of those letters. Okay? So that's it. So this is how you encode the name inside your request. So I need to learn what is the IP address of www.upmc.fr. Okay? So since this is the length is variable, they use those kind of labels that are pretty handy. And during the lab, we will see that we can even do some compression in order to skip copying this information at multiple locations in the message. So that is for the question. In the answer, or anyway, the response section, the answer section, what do we have? We're going to repeat the name, the type, the class. And on top of this, the TTL, obviously, because this is what is included in the response. The length of the data, because it depends. So for instance, if the value that I was asking is the IP address, so it's going to be 4 bytes. All right, so it makes sense? All right, so if it's the IP address. Okay, and the TTL is huge because you see it's 4 bytes. So I'll let you calculate what is the maximal value for a TTL. If it's 4 bytes, and this is seconds, what is the maximal value for a TTL? Is it month, years, second? You understand? So it's up to you to do the math and check how long can be the TTL. All right, so let's say you want to create a new record. So let's say you have a new company, you created yourself. Code, as usual, the name is foobar. All right. Yeah, 2 power 32 seconds, Alan. That's very good. How many years is this? So you just need to convert it in Google. So let's say you want to create that new company. And so as a company, you need to provide at least create a website. Okay, if the name of your company is foobar, you need to have a website, a mail server, and things like this, okay? So what does it take to create that domain? First of all, you need to ask the .com to check if foobar doesn't already exist. Okay, so .com is in charge of making sure that this domain is not already used, right? So that's one thing. Once you know that foobar doesn't exist, is not already taken, what you need? .com, the only thing that .com needs is he needs to know what are the DNS servers that you're going to install and run in your company. And so it means that you're going to add for each server that you have, and usually there's a primary and a secondary, you will add in .com 2 entries, which is 2 type NS, because those are name servers, that for the domain foobar.com, if anybody asks for to resolve one name that belongs to that domain, please reach out to this DNS server. Here's the name of the DNS server. So once you have the name, you also need to create for that server the type A. Actually, you're going to provide the IP address of the first one. So this is the first one. So this is the 2 entries that will be created in the DNS server. You're going to have a second one, and in the second one, you're going to have the corresponding information for the second DNS server that is actually installed by your company, foobar. All right? And so it means that now within those servers, what do you need? You need a type A, a type MX, and so on to allow people to either connect to your website or to be able to send you email. So you see how is it created? So that's pretty simple, right? So it means that now whoever needs to contact you, you will need first go to the root. Then you're going to go to the .com. The .com going to redirect you to one of those 2 servers, as you may ask them that, oh, I need to connect to the website of that company. Please give me this. So most of the companies, so either you can run your own DNS servers, or you can ask another company to run them for you, okay? So either you trust your IT guys and you want to pay them extra money to run your DNS servers locally, or you may even host your DNS servers to companies whose job it is to do this, all right? Okay, so as you may see now, whenever you want to use your browser, so yeah, before even doing the TCP SYN, you need to learn the IP address of the server. So you see, so even before using TCP and HTTP, on top of this, you need to do DNS. So you see, so from DNS, then TCP, then HTTP, do you see, so how many round trips do you need before you can even start connecting and requesting the object from the web server? So it takes a huge time. So hopefully caching may help also with DNS. And you remember that inside the same page, so whenever you download a page, the object may be located in another server. So it means that for a single page, if the objects are embedded from multiple other locations, you will need to do DNS queries for each of those objects if they are located somewhere else. So that takes even more time, okay? So there are many steps, and as you may see, okay, so either the cache works in your browser, so you don't need to bother. So then you need to do DNS to get the IP of the server, then your TCP connection, and then send the query and the response. So you see, so there are so many steps before you can even download. So let's go back to few points as we have 10 minutes left. So first of all, DNS is not always necessary. So what do I mean by that? I mean first that if you have a proxy, for instance, a web proxy, which means that you need to go through a cache. So sometimes if the cache is hard-coded in your proxy, in your browser, this is not your job to do the DNS. All you need is to contact the proxy, the web proxy. So this is a web proxy here. Be careful, in order to obtain an object. And the proxy will be in charge of doing the DNS request, okay? So you don't need it either if you have a web cache in your browser. So if the object is already available, you may use it right away, so no DNS. Or you may also use the DNS cache at your browser. So you see, so DNS, hopefully we have ways of avoiding it. So let's go back to what I said about the TTL. So as I said, most of the popular webs nowadays, websites, as Google or any other, are replicated. So which means that each of them run on a different IP. And we do that, why? Because we want to share the load, okay, across all those servers. So which means that now when I'm a client, I have the choice of 3 replicas. So what it means that, so either you may use different names, and you've seen this before. So either you let the user select one of the replicas by using one of the names, or what you may do is actually have a single name, and so which means that when you ask for the IP address of one of the servers, you receive not only one IP, but you receive multiple IPs. And so the idea is to say what? Is to say that, so now you ask the DNS, and you receive 3 IPs, IP1, IP2, IP3. The same with this guy. So he has the DNS, and the DNS will provide with IP. And the idea here is whenever you receive the list, the order is going to be scrambled by your DNS server. So which means that since the top one going to be different because the order going to be random, it means that by doing this, it means that somehow you hope that you're going to scramble the order, such as not everybody going to connect to the same web server. And on top of this, let's say I provided you with the IP1, but I want to make sure that the next time you need to request something as a client, please, I don't want you to go again to IP1, but I want you to go to IP2. How can you force the client from refraining from connecting to the same server again and again and again? How can you do that? How can I control which IP is used by the client as a server, as Google or CNN? What do you suggest we should do, guys? Shuffle the list, but once again, Yushen, that's a very good answer. So, but I provide you the list once. How can I now shuffle the order if I already provide you the list one time? So what I can do is have a super small TTL. And so it means that at some point, this is gonna be erased. The next time, the list is gonna be provided in a different order because it's random. So you see, so using a very small TTL will force the client to ask again for the IP of the servers, hoping that the next time I'm going to provide the list is provided in a different order. So do you understand why for Google now, it is quite powerful and to shuffle, to have very small TTLs? Having small TTLs will guarantee for Google somehow that actually is going to be able to share the load across all their servers. All right, so you see, so it's a nice trick, right? So that's what they do most of the time, okay? Okay, so obviously, one of the things is instead of doing random, so to scramble or shuffle the order randomly, you may also do some clever stuff, which means that, oh, if you know how overloaded is a server, you may provide on the top of the list the IP of the least overloaded one. But it means that DNS need to be connected to some kind of monitoring of all the servers and to know which one is overloaded. That's tricky. That's not really easy. You may also provide the IP depending on the IP of the client. So it means that, oh, I see that this guy is in France. Do I have one of the replicas? Is it close to Europe? Oh, maybe I should provide this one on top of the list. But once again, I need to know the location of the client. And as you may remember, all the clients, the IP is hidden by the local DNS. So it's really hard based on the local DNS to make sure that I know where the client is, all right? Because I cannot see the IP address of the client, or it can be based also on the route, which means that what you can do, you can say that there's some congestion in the network, so I want to provide him with an empty network, okay, without any congestion. Any other idea here? Can you suggest of any other thing that the companies are doing? Any idea? Just throw some ideas in the air. Well, you know, there are some crazy stuff that those companies are doing. So for instance, if you are in the States, so as you may know, the price of the power of the electricity vary from one state to another, right? And so depending on the surge on their data centers and how much is the electricity cost at one point of the day, they may reroute all the traffic to the state where actually power is the least expensive, right? You pay the least money for running your data center. So they do also some optimization like this, where actually the input, okay, how much is the price of the electricity, and try to optimize the bill at the end of the month this way. So this is another idea here. And yeah, there's a bunch of companies that are doing this. I mean, we're talking about a lot of money here, right? Running a data center cost, the most expensive is because of the power, right? So that makes sense. Okay, so anyway, so there are some clever stuff I can give you. So you will study this if you go for grad studies or PhDs, because those are very active areas of how to say of research. Okay, finding the best way and so on. There are a lot of things. Okay. So we already talked about DNS, so I don't really want to get into those details. Okay, we already said that small values make somehow some benefit for load balancing. But as well, if you have very small TTL, so it means that you're going to increase the stress on the DNS servers. So what is the balance here? So you see, so if you have a small TTL, you still need to wait a lot of time to resolve the DNS. So the experience of the users not going to be so satisfying, right? So what should you do? No, there's many questions like this. So anyway, so as a conclusion, so as we may see, DNS is a database, okay? It's distributed across multiple servers. And each of them are in charge of one part of the database. We call them the domains or the areas. You may read in the literature they talk also about areas, right? So those are many servers interconnected together. So we already seen how you create that overlay. So routes know the TLDs knows the authoritative and so on. And at all the levels, you have caching and you replicate the servers, all right, to make it more robust. Okay. Ooh, this is not the lecture this way. There's a U, and next week we're gonna study peer-to-peer. All right.